Hi everyone, my name is Elliot McDonald, and today I'll be walking you through the AMPL tutorial 2. When we create machine learning models, a common problem that we come across is overfitting. A machine learning model that is overfit creates predictions that work very well on the data it was trained on, but very poorly on real data. Imagine a data set where we are trying to find the relation in adult women between height and shoe size. We curate our data and train a regression model with that data. And in a model that is well fit, we're likely to see a fairly linear response that is able to see the big picture in that as height increases, shoe size increases. On the other hand, if we have a model that is not well fit, our model might simply memorize the training values that it's seen and create predictions that are very local to those memorized values. There are two popular methods that AMPL supports to combat this overfitting: three-way splits and k-fold cross-validation. Today we're just going to be talking about the three-way split method. In a three-way split, we will take the data that we curated in tutorial 1 and split it into three subsets: training data, validation data, and test data. The training data is the biggest subset, and it is the actual data that we use to train our model. You can think of training data kind of like the examples in a textbook that are used to help a student study for an exam. Then we have the validation data, which the model is not allowed to use or train with, and that way when we run our model's predictions against it, we can be sure that it hasn't seen this data before and didn't just memorize its values. We use validation data by running it against several possible machine learning models and picking the one that performs the best on this validation data. Validation data is kind of like practice examples that we use to determine what method we want to use to solve problems on the exam. Lastly, we have our final exam, the test data, which is used to simply give a final performance metric for the final model that we choose. The way that we actually divide up this data can be done in two different ways in AMPL. The first one is the more obvious method. We could just divide up the data randomly so that we have the percentage we want of our curated data in training, validation, and test, and it would ensure each of the three subsets have the same variety of types of molecules. This preferred way, however, is known as a scaffold split. In a scaffold split, we purposely group together molecules with similar scaffolding, and thus each of the three subsets are somewhat segregated when it comes to chemical families. By performing scaffold splits, we force the model to encounter entirely different types of chemicals in the validation and test sets than what they are originally trained on, which makes for a much more challenging process for the model. However, the result of the process is that models have a better ability to generalize to many different chemical families than we would get using random splits. Let's jump into the code to get a better understanding of how this works. The first thing we need to do is retrieve the curated full dataset that we put together in tutorial 1. So we import pandas and set up a string referring to the path from our Python file to the curated CSV that we saved, as well as a string for the directory we want to place the results of our split in. In this example, we're just going to put the resulting split in the same directory as the unsplit curated data. We also set the logging setting to info level to reduce the number of log messages. Many of the functions that we will use in the AMPL pipeline have us input a parameter dictionary. For the split function, we will set a variety of parameters. We set the dataset key, which refers to the string to our curated unsplit data. We name the response, chemical ID, and smiles columns that we set in tutorial 1 in the curated data frame, as well as the string to the directory for our resulting splits to go into. We specify that the data hasn't yet been split, the type of splitting method we are using, and the fraction of the total data that we want to be in the validation and test data. The remaining 60% of the data will be training data. Lastly, we set settings related to featurization and in training, which we will talk about in a future tutorial. To do the actual split, we need to import the model pipeline and parameter parser so that we can wrap the parameter dictionary and submit it to a new model pipeline object before using that object to call split dataset. The output of split dataset is the name of our split table that was saved in our output folder. By using glob.nos, we can search for the files with that UUID in the name that we just made. The split file data frame is comprised of three total columns: the ID of the compound, the subset that it was assigned to, and the fold, which has to do with k-fold cross-validation. Displaying the value counts for the subset column, we see that, as desired, about 15% of the data is now in validation set, 15% is in a test set, and 60% is in the training set. Remember that the main point of us using the scaffolding split was to ensure that the training subset was significantly different than the validation and test subsets. So we want to verify that the split actually achieved that. A handy way to measure the dissimilarity between the compounds in the different subsets is with Tanimoto distance with ECFP fingerprints. The compare split plots module can help us achieve this. We import Seaborn, Matplot, and compare split plots before reading in the curated dataset as a data frame and running split stats with the curated data, the split table, and the names of the relevant columns. We can then just take our split stats object and plot it using matplotlib to achieve a graph showing the differences between the training data and the validation data, as well as the training data and the test data. Since the majority of the Tanimoto distances are between 0.2 and 0.8, we know the training compounds are structurally different from the compounds in the validation and test sets, which tells us that we can trust the model selected based on the validation set performance will likely be generalized and perform just as well in the test set. We also want to plot the distribution of the response values in each subset to ensure that each subset has similar PKI values, so that the model wouldn't be asked to predict a value from the test set with PKI value different than anything it's ever seen before. We can do this by importing split response dist plots and supplying the plot split subset response distributions with the split parameters. Since we can see that the PKIs are roughly similarly distributed across the subsets, we can be confident that this won't be an issue. We have now finished the process of splitting our data, and in tutorial 3, we'll lead you through the process of training a model using this dataset. Thank you.